Hi everyone, this is Siddharth. For problem 3 from the current homework, I thought I should give a different perspective on the way this problem has to be approached because the way it's talked about in the problem in the handouts, the introduction to noise handout that Professor Lee has uploaded, it talks about reciprocity, and I find that most of the students, because they don't have a clear understanding of how reciprocity works in networks, will have a difficult problem in understanding that. So I thought I'll give a different way of solving this problem. But before that, just to clear the air on what you mean by an attenuator with a attenuation of L, what I've shown is a simple two-port network here, which is an attenuator of loss L. It is conjugately matched to the source, which is basically nothing but a source of sinusoidal RMS Vs and a source resistance Rs. Because it's conjugately matched, you see Zn equal to Rs. The power available from the source is, you can compute that because Vs is the RMS voltage. You can have Vs square by 4Rs as the power available from the source, and because these things are matched, Pn is equal to P available of S, and so that's the amount of power that all the maximum available power goes inside the attenuator. Now what's available at the attenuator at the output, and this is again the available power, which basically means that whatever the Z out of this circuit be, if you match it with another Z out here, you would get a power available out at the output to be Pn by L, which is P available S by L. L here is a number greater than 1, so that's the attenuation. Equivalently, the gain of the system is equal to 1 by L, and that's less than 1. Now let's talk about what happens when you have, say, for the purpose of measuring noise figure, what you're going to do is you're going to load this attenuator with a resistance Rs again, and then that is going to have its own Rs, and it's going to have its own En square by delta F, which is equal to 4 kT Rs. Now we know from the analysis in the class that the power noise available from the source is equal to kTb, where B is the observation bandwidth. Now all that power goes inside, so now your power input is equal to kTb. So assuming that this attenuator is completely noiseless, the only noise coming in from this resistance Rs, what is the P noise available at the output when attenuator is noiseless? So I won't give you that answer. The Pn is kTb, and go up here and see what the answer is going to be. So that's this number. Now think about what happens when the attenuator is taken to be noisy. Now what is the attenuator made of? So let me just redraw that circuit again and say that this is the En square by delta F, which is 4 kT Rs, and that's Rs. And I'm going to draw a slightly bigger picture. The attenuator is resistive, so it has resistances connected. It's a network. I don't care as how those resistances are connected and what the values are, but this is how it is. So given that everything is at the same temperature T, I can represent each of these resistors by either their voltage things. For some I can have currents. I'm representing the corresponding voltage, equivalent voltage noise circuits. Now given this whole information at a particular temperature T, and given the following information that if you have two resistances in series, R1 and R2, with their own voltages of 4 RMS, the noise voltage density squares as 4 kT R1, 4 kT R2, given that this is equivalent to one resistance of 4 kT R1 plus R2, and similarly if you have, say, two resistances in parallel with their own currents like this, 4 kT by R1, 4 kT by R2, R2 and R1 is equivalent to just one resistance and an equivalent current of 4 kT by R1 parallel R2. Now given all this information, what I can do is I can represent this whole block looking out at the output as nothing but one equivalent resistance, which is the R out, and its own equivalent noise current ER out square by delta F, which is equal to 4 kT R out. So now what is the power? So the power in the noise power at the output, which is going to be available, I should say available output for the whole system, is how much? So you should be able to compute this value. So if you have done that effectively, now you have the noise figure of the attenuator to be the power available at the output because of the whole system, whole system, which is basically the power available in this case, which I showed is equivalent to the power available in this case, right? Was divided by the power, the noise power available at the output only because of the source resistance, which is the same as saying that you are driving the attenuator, which is assumed to be noiseless, with a source resistance Rs, and you should get this number here, uh, noiseless attenuator, and that should give you L as the attenuation. So this is what you had tried to prove, that noise figure is equal to L, and it can be proved by the simple method where you have to just find out these numbers. I'm just falling short of giving you those numbers, and I hope you don't face a lot of problems in doing that. Anyways, thank you.